So let's talk about a really cool and surprisingly simple idea from the world of AI called hill climbing. Think about it for a second. How do you solve a problem when you can't see the whole picture? How would you find the highest peak in a huge mountain range if you were stuck in a really thick fog? Well, today we're going to figure that out. All right, here's the game plan. We'll kick things off with that climbing in the fog idea to get the intuition down. Then we'll dive into what the algorithm actually is. We'll watch it work on a simple graph, and then we'll really put it to the test with the famous 8 queens puzzle. And this is super important, we're also going to talk about when it all goes wrong. And finally, we'll wrap it all up with the key things you need to remember.
Okay, so to really get a grip on hill climbing, let's just forget about computers and code for a minute. Let's start with a really powerful analogy. Because at its heart, this algorithm is all about one thing: making the best choice you can with the information you have right now.
I want you to picture this. You're a hiker. Your goal is to get to the highest peak you can. But there's a catch. You are completely surrounded by a dense, thick fog. You literally can't see more than a few feet in any direction. So, what do? What's your strategy? Well, probably the most logical thing you could do, right, is to just feel the ground around you. Find the direction that goes up the most, the steepest path, and take a single step in that direction. And then, from your new spot, you do it all over again. You look, you feel, and you take the steepest step up. That very simple, repetitive idea, that is the soul of the hill climbing algorithm. Okay, so the foggy mountain analogy is great, but how do we actually turn that into something a computer can understand? How do we translate things like elevation and steepest step into actual code? Well, the first thing we need is a way to measure our height. For our hiker, that's their altimeter, right? It tells them their elevation. In an algorithm, we call this an objective function, or sometimes a fitness function. It's just a tool that takes any possible solution to our problem and gives it a score. It tells us how good it is. And our goal is always to find the solution that gets the highest possible score. So the algorithm itself is dead simple. Here are the steps. 1. You start at a completely random spot. 2. You look at all the places you can get to in just one step. We call these neighboring states. 3. You move to the neighbor that has the best score. And 4, you just repeat. You keep doing that over and over until you get to a spot where every single neighbor has a worse score. Once that happens, congratulations. You've found a peak and the algorithm stops. All right, enough theory. Let's make this real. We're going to walk through a really simple climb using a graph so you can see exactly how this thing behaves in the wild. So I want you to think of this graph as our whole mountain range. The horizontal line at the bottom, that's what we call the state space. It's just a fancy way of saying all the possible answers to our problem. And the vertical line, the height, that's our objective function. It's measuring how good each of those solutions is. Our ultimate goal, of course, is to find the absolute highest point on this curve, what's called the global maximum. Okay, so let's say we start right here, at the current state. The algorithm looks to its left and to its right, and it sees that the path to the right goes up, so it takes a step. It does this again and again. It's always climbing, always moving to the highest valued neighbor. It keeps going until it gets right here to this local maximum. Now, from this spot, every direction is downhill, so the algorithm stops. And right there, you see the problem, don't you? It found a peak, sure, but it completely missed the highest peak. And we're about to see why that's such a big deal. Okay, that graph was a nice little warm-up. But now let's throw a much more complicated challenge at our algorithm to see how it holds up. Let's talk about the famous 8 queens problem. So the goal is pretty straightforward. Place 8 queens on a standard chessboard so that no queen can attack any other queen. Now, for our algorithm, a state is simply any board that has one queen in each column. A neighboring state is just any board we can get to by moving a single queen up or down within her column. And how do we score it? Well, our objective function just counts how many pairs of queens are attacking each other. And here's the twist. This time, a lower score is better. The perfect solution, the goal, is a score of 0. So how does it start? It doesn't use any fancy strategy. It literally just plops 8 queens down on the board randomly, one in each column, just like this. This becomes our starting point, our initial state. From here, it's going to calculate the score and start climbing, or in this case, descending, towards a better solution. Now, you might be thinking, why not just check every single possibility? Well, because even with the rule of 1 queen per column, there are almost 17 million different ways to arrange the queens on the board. Trying to check all of those, what we call a brute force search, would take forever. Hill climbing is our attempt to find a solution much, much faster.
But just like we saw with that graph example, our foggy hiker's simple strategy has some pretty serious blind spots. So let's talk about the common ways that the hill climbing algorithm can get completely stuck. This slide shows the two big ways our hiker gets lost. On the left, we've got a foothill, or what's technically called a local maximum. See, the algorithm climbs up this smaller peak, gets to the top, and thinks it's done. It has no idea the real goal, the global maximum, is right next door. And on the right, you see a plateau. This is a big flat area where there's no clear up direction to follow, so the algorithm just wanders around, totally lost.
So how much of a problem is this, really? Well, for the 8 queens puzzle, the most basic version of hill climbing fails a lot. It fails to find a solution 86% of the time. It gets stuck on one of those little foothills and just gives up. That means it only solves the puzzle in about 14% of its attempts. That's not great.
So it's pretty clear the basic algorithm has a massive flaw. But you know what? The story doesn't end there. Let's look at a really simple but incredibly powerful tweak that makes it way better before we sum up what we've learned.
The biggest problem is getting stuck on those plateaus, right? So what if we change the rules just a little bit? What if when the algorithm hits a flat area, instead of giving up, we let it move sideways to a neighbor that has the exact same score, just hoping it might lead to a new upward slope? And wow, check out these results. They are absolutely staggering. Look at this. Just by allowing the algorithm to make up to 100 of these sideways moves when it gets stuck, the success rate for the 8 queens problem shoots up from a measly 14% all the way to 94%. That is a huge, huge improvement from one tiny little tweak to the rules.
Okay, so let's wrap this up. What are the key things to remember? Hill climbing is what we call a greedy algorithm. It's always making the choice that looks best right now, in the moment. It's super simple, it's fast, and it barely uses any computer memory. But here's the most important takeaway of all. While it's fantastic for finding a good enough solution really fast, it gives you absolutely no guarantee that it will find the absolute best solution.
And finally, here are the common traps to avoid. The number one mistake is assuming it always finds the perfect answer. It doesn't. You always have to be thinking about those local maxima, the foothills, and those flat plateaus. And remember that simple tricks, like allowing sideways moves, or even just restarting the whole search from a new random spot if you get stuck, can make this algorithm way, way more powerful.
And all of this leaves us with one final, very practical question to think about. Hill climbing is fast, and it's simple, but it's imperfect. So it kind of forces us to ask, in our own work or even in our own lives, when is a good enough solution that we can find right now actually better than a perfect solution that we might never find at all?